Okay, so today this lab we're going to do is probably one of the more complex labs, and it's fairly time consuming. But it's also the sketchiest lab that you're going to do in terms of the results. Most of the labs we do, absolute home runs. This lab, sketchy. And here's the reason why. So basically what you're going to do is that you're going to start off with a certain compound of manganese 7. So the cool thing about manganese is that manganese, more than about any other metal, has the capacity to exist in different oxidation states, okay? So, and as it goes through those oxidation states, it changes color, okay? So what you're going to do is you're going to start off with manganese 7, because that's oddly enough the most stable form. And so what we're going to do is a series of what we call redox reactions. So redox is short for reduction and oxidation, okay? So you take Chem 2 or AP Chemistry, literally we spend entire weeks talking about redox reactions, okay? So reduction and oxidation, I'm going to give you the precursor on how you remember this. It's like the lion. Leo, the lion, says grr, okay? So Leo, this start, says something, if you lose electrons, okay, that's oxidation. If you gain electrons, then that's reduction. So whenever you kids, you can always tell when kids are taking a redox test, because they're sitting there going, Leo says grr, Leo says grr, Leo says grr. Okay, so you can't have just an oxidation reaction, you can't just have a reduction. So basically, redox reactions take place because there's a tug of war for electrons, okay? So when something's going to lose electrons, something's going to gain electrons. That's how it works, because you just can't gain, or it has to go, that electron has to go somewhere. So this is why they're called redox reactions. Not reactions, not ox reactions, the redox reactions, because you have to have both going on at the same time. So what you're going to do, this lab, is one big continuous redox reaction. So now, here's the other thing I'm going to emphasize. You are going to be dealing with some exceptionally caustic chemicals today, concentrated sulfuric acid, permanganate, ions that will stain your clothes, get in your eyes. You absolutely, from the second you get in that lab and you start to get things around, you put on those safety glasses, okay? Without fail, I will have no tolerance whatsoever for not wearing safety glasses today, because there's so many things that can go wrong in terms of your eyes, okay? So, and if you're wearing nice clothes and you're worried about getting something stained, there's those lab aprons there, you might even put those on, okay? So I'm just saying. Mainly because literally, I can't tell you how many pairs of pants, shirts I've ruined over the years. Like, here's this, you get like one drop on it, especially like concentrated acid or concentrated base. You don't know it until you wash it, and then there's like this hole in your pants or in your shirt where you got something on it. So it isn't like it's, oh, I got an acid, drop of acid on your clothes are immediately going to start to smoke. That's going to be bad. But, so I'm just telling you, if you're worried about your clothes, okay, put that on. But I'm telling you right now, I will have no tolerance, zero, zip, no tolerance for someone not wearing their safety glasses today, because you're dealing with such caustic chemicals. Now, the other thing that's going to happen as you go through this is that you are going to have different concentrations. You got to pay attention to masses, things like that. Some of these volumes and masses that you measure out, they're kind of close. Other ones have to be very exact. So, for example, on the first thing you're going to do for this pre-lab is that what I want all of your glassware labeled. So you're going to, the purpose of this, you're going to look at the different oxidation states of magnesium all the way from 7+ to 2+. So, because you want to make sure that you have your glassware out and labeled to begin with. So on this first one, notice on this one, I tell you to measure out 0.10 grams of potassium permanganate. So potassium permanganate has that formula, KMNO4. So here's how you know that the oxidation state of manganese right now. So how many valence electrons does oxygen always have? How many valence electrons does oxygen have? For the love of God, please someone answer this question before I completely have an aneurysm.
6.
Parker, save me.
6.
Thank you. How many does it want?
8.
8. How many is it going to gain?
2.
So what's the oxidation state of oxygen?
2 minus.
2 minus, right? So here's the deal. So you have 4 oxygens, each of those at -2. So that means this thing is -8. Potassium has 1 valence electron, so it's going to lose that one, so that's +1. Now, everything has to add up to equal to 0. So what's the oxidation state of manganese in the potassium permanganate ion? So it's an algebra problem. 1 plus something plus -7 adds up to equal to 0.
+7.
+7, okay? So what's going to happen is that the initial state of the permanganate ion in this situation is 7+. So what this means is that we've lost a whole lot of electrons. So because there's such a deficiency of electrons, what happens is that this thing is going to look to gain electrons. So as it gains electrons, and basically that's what we're going to do. What we're going to try and do is we're going to try and let manganese gain electrons in stages, okay? We don't want it to go all the way from 7+ to 2+ all in one step, okay? It's like a pendulum. We're over here at 7+. We want to end up over here at 2+, but we don't want it to go all at once, okay? Instead of one continuous swing, we want it to go basically like in steps. We want to go from 7+ to 5+ to 4+, okay? And each one has a unique color. Now here's the problem. Without going through a whole bunch of math, these equilibriums exist within very, very, very tight tolerances. So if you shift this equilibrium one way or the other, then that particular color might not show up. And some are pretty easy. This one, absolute home run. So when you look at this potassium permanganate, it almost looks like finely ground dark purple pepper. Okay, it's a very, very fine powder. Don't get it on your fingers, okay? Because of the fact that it will completely stain your fingers, because what's happening is that this Mn is looking to take in electrons, okay? And if your skin is available, that's where it's going to take its electrons from. This is why, especially with potassium permanganate, you never, ever, ever touch it with your fingers. You never, don't get it in your eyes, because if you get it in your eyes, that's going to become the source of your electrons, is your eyes, and that's not going to end well, okay? So I'm telling you, with this stuff, you have to be very, very careful. So notice on here, you're going to measure out exactly 0.10 grams, okay? Now 0.11, I emphasize 0.10. This has to be exact, because what we're going to do is we're going to use this solution as the beginning of everything else that we're going to do. So if this molarity is wrong at the beginning, everything else is going to be wrong going forward. Okay, so that's why it's so important that you get this right. Now, then you're going to measure out 60 milliliters of distilled water. Notice I say not 60. Okay, I didn't say 60, get about 60. Notice I said 60.0. Okay, so you might have to, you don't have a 60 milliliter graduated cylinder. You got a 25. Oh, do 25 twice, get you 50, get 10 more, boom, there you go. So you're going to mix the water in a 100 milliliter beaker, and then you can take a short test tube. Now, one of the things you'll see, some of these are going to do with short test tubes, which is the ones that you all have. Some of them, I need you to use tall test tubes, okay? So that's another thing. Short test tube, tall test tube. Pay attention to what size of the test tube I'm telling you to use. So you're going to take this, you're just going to fill it about half full, and you're going to set it aside. You're done with that. So you're going to have a short test tube, and you're going to label that Mn 7+. Okay, that's all you have to do. That's Mn 7+. You don't have to do anything with that. So this is going to be an example. You're going to make a list of your glassware. Okay, and the glassware is going to say, oh, a short test tube, and that's going to be labeled +7. Okay, so that way you know, okay, this is what I gotta have. Then you can take a tall test tube. Okay, I got tall test tubes over there. They're about like yay. Okay, and you're gonna label that 6+. So then over here you're gonna put, oh, I need a tall test tube, and I'm gonna label that 6+. So to do that, you're gonna take 3 milliliters of your 0.01 molar solution of potassium permanganate from, okay, and you're gonna put that into a tall test tube. So you're gonna take your little graduated cylinder, and you're gonna measure out 3 milliliters of that, and you're gonna put that into that tall test tube. Then you can take a 10 milliliter graduated, and you're gonna put 1.2 milliliters of a 1 molar solution of sodium hydroxide to the test tube. The sodium hydroxide is gonna be in a dropper bottle on your lab station, okay? And again, you need to measure out 1.2 milliliters of this stuff. So then you're gonna add 0.01 molar sodium sulfate, okay? Na2SO3, sodium sulfide, and until a green color appears. This will take approximately 5 to 20 drops. Here's the problem. This is why I say there's such variance in this. Depending upon the size of the drops, depending upon the concentrations, this is the sketchiest one to try and get, okay? Is this one that's gonna be 6+. So basically what we're trying to do is we're trying to take 7+, and we're gonna try and make it gain just 1 electron and turn into Mn6+, okay? So that's what we're trying to do. We're trying to get it to gain exactly 1 electron. That's why this thing has such small tolerances in terms of an equilibrium, okay? So then once you get that done, hopefully, it turns to green. That's the sketchiest one. Should be okay. Now, then we need over to step 3. Now we're gonna try and make Mn5+. Okay, so now we're going in steps. So now, you can take away dang, you're gonna measure, now this one, I say you're gonna measure out about 2 grams of potassium hydroxide pellets. Here's the difference in how I wrote this lab. Notice with the potassium permanganate, I said you need 0.10 grams. You need exactly that value. This one I said, yeah, you need about 2 grams, okay? Potassium hydroxide, or they look like kind of like BBs, it's a bigger pellet, okay? That's why it's tough to get that. So get something around 2 grams, 2.1, 1.99, something like that, okay? So then you can put those in 100 milliliter beakers. Then you're gonna add 1.5 to 2 milliliters to the 0.1 molar potassium permanganate and stir until all the potassium hydroxide dissolve. If the pellets don't dissolve after stirring 1 milliliter, add stir, okay? So then, there's some conditions there. And again, I can't say, oh, this is what you're going to do because of the fact that it kind of depends upon how much potassium hydroxide you have. So there's some conditions there about how you're going to handle this, okay? And again, then you're going to put this into a short test tube labeled Mn5+. Oh, so then you can have a short test tube +5, okay? So then, now, down here, now we're down to a specific amount again. Now you're going to measure out 2.01 grams of MnCl2, manganese chloride, in a weighing dish. It's like a pink granular substance. Most of the time, the powders that we deal with are white. This is actually like kind of a pinkish orangish color to it. So again, notice that says 2.01 grams. If you can't get exactly 2.01 grams, don't flip out, okay? But try and get it close to that as you possibly can. So then, on this one, notice I want you to measure out, again, exactly 20 milliliters of water. So this is an exact amount. So, combine the water in a 100 milliliter beaker, label this beaker 0.80. So now you're going to go, oh, I'm going to need a beaker, okay, and that's going to be labeled 0.80 MnCl2. So we're going to take this stuff, it's soluble, it's going to dissolve. Now we have a certain molarity, okay? So then you're going to take 9 milliliters of that, put that into a tall test tube again. So now we're back to a tall test tube. And add your 1 milliliter concentrated sulfuric acid. Sulfuric acid, and there's going to be a dropper bottle of that on your lab station. And it's going to say like 6 molar H2SO4. So sulfuric acid is H2SO4. Hydrochloric acid is HCl. Okay, so those are the 2 acids that you're going to be dealing with. So basically, what happens to make redox reactions happen, a lot of times they have to happen in what we call an acidic environment. An acidic environment just means that you need a whole bunch of hydrogen ions available to you. So these aren't involved in the reaction, they're just producing the hydronium ions that you need to make the reaction take place. So that's all they're doing, is they're just saying, hey, this reaction is going to take place, we need a bunch of hydronium ions, that's what the acid is doing. Okay. So then you're going to add this 0.01 molar potassium permanganate dropwise until a rose color appears. This is also one that's a little bit sketchy, okay? So in an ideal world, when this gets done, it almost has like a very faint, diluted cherry Kool-Aid look to it, okay? Almost like, it's going to kind of look like Addie's sweatshirt, okay? That's what it's kind of going to look like in a best case scenario, all right? Best case scenario. Sometimes it might be a little bit darker, sometimes it actually looks like mud brown, okay? But again, these are ideal situations, but literally, if this equilibrium shifts by like 1 drop, you don't get this particular color. So I'm not real uptight that you don't get these exact colors. I'm more concerned that you get the process down. And then you're going to label a short test tube labeled Mn2+, filled half full with 0.8 molar magnesium from step 5. Label this Mn2+, place it in the test tube rack. So what's going to happen in an ideal world, when you get done, you're going to have a test tube rack, and you're going to have all of these test tubes in there, and you're going to have this spectrum of colors. That's the end game, okay? That you start with these, you go through, boink, 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 you go all the way from 7+ all the way down to 2+, okay? That's the idea. So when you get done, you can call me over and go, look, here's the different oxidation states of manganese. And like I said, sometimes this works beautifully, other times, literally 1 or 2 drops just wrecks this whole thing. But what you're going to see, and this is the most important, okay? This is the most important. When you prepare this 100 milliliter beaker, okay, this very first thing that you're going to do, this is the one that has to be right. Because if this beaker, and that's the first thing that you need to label, is a beaker that says 0.1 molar potassium permanganate, because if that's wrong, everything else that you're going to do with that is going to be wrong. So this is something that you're going to keep going back to again and again and again. So don't come to me later on in the lab where it says, like for example, on step 2, it says place 3 milliliters of a 0.01 molar potassium permanganate. Don't come to me and say, Mr. Burkamp, where's the 0.1 molar potassium permanganate? That's what you prepared. That's what you're going to mix up first that you're going to use later on, okay? So you're going to mix that up. And if that's wrong, everything's going to be wrong from there on out, okay? Got that idea? So, literally, when we get over there, okay, get with your groups, go through here, get your glassware labeled, okay? Do not even start at the lab. Get all these test tubes laid out, get your beakers laid out, get all those labeled. I'm going to have labeling take over there. I'm going to have some tall test tubes, the short test tubes are already in your rack. Get all that done, then actually start the lab. Now, as you go through this, with your lab groups, you might divide and conquer. You might say, hey, why don't you start mixing, look ahead. Why don't you get the MnCO2? That way we'll all have that ready. Maybe have somebody go ahead, hey, you go get the potassium hydroxide, okay? So that way you have that ready later on. So this takes a while, mainly because of the fact that you have so much to prepare and everything else like that. And as you're counting these drops, you're going to add a drop, stir it. Make sure that if you're using that stirring rod, that you wash that stirring rod in between different solutions, okay? Otherwise, you're going to cross-contaminate this thing, and it's going to be an absolute train wreck, okay? So, this is the only time I will ever tell you this. I cannot guarantee the results of this lab, okay? But what I can't guarantee you is that, so help me, if I see you without your glasses on, you will have no warning. I'm just gonna send you back to this room, okay? Because it is that important in terms of the things that you're gonna be dealing with. You don't have to have your glasses on when you're like labeling the glassware, but as soon as you start to touch a chemical, you get those glasses on, okay? Are we good? Fantastic. I have great hope. Let's go do science.